and we'll sort of go along as we do this. So first, determine the number of total valence electrons in a compound. It is the sum of the number of valence electrons of each atom. For ions, add or subtract the appropriate number of electrons as designated by the charge. Okay, so it sounds like first we need to take a look at the compound that we're going to be writing it for. So this is CH3OH. This is methyl alcohol. Inorganic chemists might take a look at this and say, wait a minute, why wouldn't this just be CH4O? I thought we combined those hydrogens. Well, this is actually written in a way where it gives you a little bit of a hint in the kind of connectivity of this compound. And we'll talk more about that in a second, but it's a really extraordinary thing, and organic chemists love to do this. Okay, so let's just get step one over with. We got carbon, we have 4 hydrogens, and we have an oxygen. So carbon has 4 valence electrons. Hydrogen has 1 valence electron. Remember we were looking at that. So carbon is 4, hydrogen is 1. But because that we got 4 hydrogens, then we multiply that by 4, and oxygen is 6. So 6 plus 4 plus 4 equals 14. So that should be the number of valence electrons that we have when we complete the structure of this. Okay, step 2, determine the conductivity of atoms. Be careful of isomers, or compounds with the same formula but different arrangement. Okay, so at this level you probably don't have to worry too much about isomers. We try to avoid those. But looking at this CH3OH, this actually gives us a big hint. Organic chemists write out compounds where it can tell us how the compound looks. So basically 1 carbon at a time. So this is how it's going to be arranged. CH3OH. That makes a lot of sense, because if you tried to write it out this way, it's inevitable that you're going to have some people try to do that. And it just doesn't work that way. So that's a pretty good connectivity right there. Okay, so step 3. Connect atoms with single bonds and arrange remaining electrons in lone pairs. Assure each atom has 8 electrons surrounding it, except hydrogen. We talked about that for the last one. Hydrogen is a rule breaker. It likes to have 2. So let's add single bonds here. That looks pretty good. Now we need to add lone pairs so that each atom has 8 electrons, unless it's hydrogen. So carbon here, it's already got all 8 of those electrons that it wants. Oxygen, though, only has 4. So what we can do is we can add 2 lone pairs to oxygen, and that will fix our problem. Okay, so each pair of bonding electrons can be shown with a single line. Lone pairs are shown with dots. So now we can finish up the touches. And that is our complete Lewis structure. And number 5 says that we need to double check it by counting the number of electrons in it and seeing if it matches up with this number that we got up here. So remember that each line represents a bonding pair, so we count those as 2. So 2, 4, 6, 8, 10, 11, 12, 13, 14. That agrees with up here. So this is the correct Lewis structure for methyl alcohol CH3OH.